When it comes to these laws of definite and multiple proportions, sometimes they sound so easy, and then sometimes when I'm working my way through them, I end up chasing my tail. So I thought I might explain a little bit more than Wiley does in the book to give you a handle on them. Let's look at these. So, the laws of definite proportions is also sometimes called the law of definite composition. So allow those to be the same. And then the other law is the law of multiple proportions. So about 1800, Joseph Proust made this conclusion that a given compound always contains elements in certain proportion by mass. So the thing to hone in on here is we're going to talk about weighing elements that have composed a compound. So imagine that you had some way to, and this is exactly what they did, they would take a compound and they would break it up into its constituent elements and weigh them. And so this is all going to be about the mass of these elements. So the law says this, that atoms combine in whole number ratios. So their proportion by mass. Keep in mind, we're going to talk about weighing things and how much the mass is, not the number of things at this point, but the mass will always be the same. So for example, water is made up of 2 hydrogen atoms and 1 oxygen atom. That means that they combine in whole number ratios. Well, when we are talking about the law of constant composition or definite proportions, um, we're not thinking about how many hydrogen atoms and how many oxygen atoms are come together, but we're talking about the fact that if you knew something about the masses of them, that those masses would have simple whole number ratios. So, for example, the ratio of oxygen to hydrogen in water is always 16 to 2. Now that 16 to 2 number comes from the fact that if you would look up oxygen in the periodic chart of the elements, that oxygen has an atomic mass of 16. And because there are 2 hydrogens, and each of those hydrogens have an atomic mass of 1.01, we end up with the equivalent of 2. So 1.01 times 2 is still going to give you 2. So if we simplify that, now we have the ratio of 8 to 1. And so the masses that we're talking about will always have a ratio of 8 to 1 whenever you're dealing with hydrogen. Here's another example. So here, potassium chloride. Potassium chloride always contains 1 atom of hydrogen for every 1 atom of chlorine. So we're not going to be talking about the number of atoms really when we're talking about this law. We're going to talk about the mass of that 1 atom of potassium and the mass of that 1 atom of chlorine. And when we do that, potassium and chlorine always have a mass ratio of 39.09. Where does that 39.09 comes from? Well, if you look up potassium in the periodic chart of the elements, it has an atomic mass of 39.09. If you look up chlorine in the atomic mass, or the on the periodic chart of the elements, sorry, it has a atomic mass of 35.45. So these numbers look almost alike, but this is 1.1 to 1. So if you would take 35.45 and divide that by 35.45, you get 1. If you take 39.09 and divide by 35.45, you get 1.1. So the mass ratio is going to be 1.1 to 1 when you have chlorine. Or when you have potassium chloride. All right, so now we're going to move on to the law of multiple proportions. This was proposed by John Dalton. And it's similar. It has its basis on the law of definite composition. It says when the same 2 elements combine to form more than 1 compound, here's what he believed would be true. the ratios of the mass of one element in the first compound to its mass in the second compound, as it is combined with the same mass of the other element, can always be expressed as ratios of small whole numbers. Okay, so once again, we're going to be dealing with the masses of these elements, not the number. There's a relationship between the mass and the number, but we're going to be dealing with the masses of these elements um, with one another and um, with the, let me back up. So we're going to deal with the mass of one element in the first compound to the mass of that same element in the second compound. That's what I really should have said. So let me show you an example. It'll make more sense here. So carbon combines with oxygen in carbon monoxide as well as carbon dioxide. So in order to solve this problem of multiple proportions, what we have to do is we have to keep one of the two elements, they have to maintain the same mass. So here, carbon, there's only one carbon here, and carbon's atomic weight is 12.01. So because there's only one carbon in this compound, we also have 12.01 grams of carbon. So we've kept the mass of carbon the same, but our mass of oxygen is going to change. The first one only has one oxygen, and if you look up oxygen in the periodic chart of the elements, it says it's 16 atomic mass units or 16 grams per mole. And then this one here has two, so it would be twice as much as that, 32.00 atomic mass units or 32.00 grams per mole. And so now you can see the simple whole number ratio between these two. They're 1 to 2. So whenever we're dealing with the law of multiple proportions, we have to hold one of the elements, we have to hold their mass constant, 12 and 12, and then compare the mass of the other one to figure out what their ratio is. All right, so let's look at a quick practice problem along that line. So we have two different carbon compounds. One is called ethane, and it's C2H6, and one is called ethene, and it is C2H4. Well, we want to know what the lowest whole number ratio of hydrogen atoms is that react with the same number of carbon atoms. So what we have to do is we have to say that we have two carbon atoms in both molecule, and that's pretty handy, and we do here, so we don't have to change anything there. And we're going to, and so we know the mass of those two. We can look up carbon, and we can say that that's 24 grams for each of those, well, 12.0 each. So there's 24 grams of carbon in this compound and 24 grams of carbon in that compound. So we're going to hold carbon the same, and we're going to look now at the mass of hydrogen. So let's go ahead and explore this a little bit with some math here. All right, so here I put that problem on a spreadsheet. So here's my carbon, and the first compound is C2H6. My second compound is C2H4. In both cases, both compound A and compound B, I have 24 grams of carbon because I looked carbon up on the periodic chart of the elements, and there's 12 grams per mole, or 12.0 atomic mass units for each carbon, and 24 for the two. So those are going to be held constant. Now my only question is between hydrogen. And I know that I have 6 hydrogens in one case and 4 hydrogens in the other. And so what I'm going to have to do is figure out the mass of those 6 hydrogens to start with. And to do that, I know that the atomic mass of hydrogen is 1.01, so and I have 6 of them, so I multiply 1.01 times 6, and I come up with 6.06 grams, or 6.06 atomic mass units for that hydrogen. And I'll do the same thing. I got to convert the 4 hydrogens into their mass too. So if I do that, I take the 1.01, which is the atomic mass of hydrogen, multiply it by 4, because I have 4 of them, and that gives me a atomic mass units of 4.04. So now I am comparing grams of hydrogen to grams of hydrogen, not numbers of hydrogen, but grams, okay? And if I just divide the larger one by the smaller one, so if I take 6.06, divide that by 4.04, I end up with 1.5. And then if I take the smaller one, divide it by itself, uh, that's pretty simple. 4.04 divided by 4.04, I end up with 1. So now I know my ratio is 1 to 1.5. But if I want a simple whole number ratio, I've got to now convert those into whole numbers. And to do that, if I just multiply both of them by 2, I end up with a simple whole number ratio. And so that's going to give me my answer to the question. What's the simple whole number ratio of hydrogens to carbon here? And that would be 3 to 2. And sure enough, our answer is 3 to 2. All right, let's do another practice problem. Here I have carbon reacting with oxygen to form two compounds as shown. Carbon A has, or compound A has 2.41 grams of carbon and 3.22 grams of oxygen when we analyze it. Compound B has 6.7 grams of carbon and 17.9 grams of oxygen when we analyze it. So there's a variety of ways that you can solve this problem. But the first thing we want to do is we want to figure out what are we trying to solve for. And we want to know what the lowest whole number ratio of carbon is to oxygen. So in order to answer that question, we're going to have to get our oxygen mass to be the same for each of these, because right now I have two different masses, 3.22 grams and 17.9 grams. And one of the ways, it's a simple way to get these to the same mass, is just to figure out what would it take to get 3.22 to 1 gram, and what would it take to get 17.9 to 1 gram. If I can change both of these numbers to 1 gram, then I'm working with something possible. And so all I have to do to get 3.22 to get to 1 gram would be divide that by 3.22. And if I divide 3.22 by 3.22 to get 1 gram, I've also got to divide 2.41 by the same amount. So we'll have to divide that by 3.22. And we're going to come back to that number. I've got to get 17.9 grams to 1 gram. How do I do that? Well, I can divide that by itself. 17.9 divided by 17.9. So now I've rendered this number 1 and I've rendered that number 1. And that number there, I've got to take it and divide it by 17.9 to get so that I've made the same change to this number as to that number. And that's the strategy that that is recommended here. You find the grams of carbon per 1 gram of oxygen for each compound. And then you divide the highest answer by the smallest answer. And let's look at the spreadsheet again just to see if we can follow that. All right, so here I've just kind of rewritten the question. I have two samples. One sample has carbon at 2.41 grams and the other has carbon at 6.71 grams. One sample has oxygen at 3.22 grams and the other oxygen at 17.9 grams. Let's go back and make sure that I copied that correctly. 2.41, 6.71. Is that right? 2.41, 6.71, yep. And 3.22 and 17.9. 3.22, okay, so I got my numbers right. All right, so I'm going to move all of my oxygen to 1 gram. And to do that, I'm just going to say that I have 3.22, divide that by 3.22. And no surprise, well, I didn't do that right. Try that again. 3.22 divided by 3.22. That's what I want to see. And because I divided that by 3.22, I'm going to have to do the same thing here. I'll take that 2.41. I'll say that I have copy. Yeah. 2.41. Divide that by 3.22, and that gives me that answer. And I got to get this one to 1 gram too. So I'm going to say that that is equal to 17.9 divided by 17.9. So that's going to be 1 gram. And this one here is going to be 6.71 divided by 17.9. There we go. And so now I have got my oxygen the same, and now I'm just going to look for the mass ratio with my carbons. And so to figure out what that is, I'll take the smaller of the larger of the two and divide it by the smaller. So I'm going to say that this is going to be 0.7. I'm just going to round that to 748 and divide that by 3.75 or 0.375. And did I do that right? No, I didn't. It's 7.748. There we go. See, I make every mistake you could imagine. So that's almost 2. And then if I divide 3.74 divided by 3.74, we know that that's going to come up to 1. So I have a ratio of 1 to 2 at that point for our carbon. And so if we go back to our PowerPoint, and if I want to see what my answer is, should be, yeah, answer 2 to 1. Right, let's do one more practice problem. All right, so now I have 2 different compounds, compound A and compound B. Both of them have lead in them, and both of them have oxygen in them. That's essential. If you're going to do these kind of problems, you have to have 2 compounds with only the same elements in it, just in different combinations. So compound A has 2.98 grams of lead and 0.461 grams of oxygen. Compound B has 9.98 grams of lead and 0.763 grams of oxygen. Well, for a given mass of oxygen, so we were going to try to get oxygen to be the same, and we'll follow the same exact strategy. We'll figure out what we have to do to get this first one to equal 1 gram, and then figure out what we have to do to get the second one to equal 1 gram, and then we'll be able to compare the ratio of our lead. For a given mass of oxygen, what's the lowest whole number mass ratio of lead in the 2 compounds? So we want to know what these is. So we've got to hold oxygen constant. And to do that, we have to get them constant. And let's see how we could do that. All right, now here's our 2 samples of lead oxide. 2.98 grams and 0.461 grams, 9.98 grams and 0.763 grams. So those are our 2 samples. We want to get both of these to 1, and so to do that, we'll take 0.461 and divide it by 0.461, and that'll give us 1, obviously. And then we need to take then 2.98 and also divide it by that same 0.461 to reduce this amount. And then we will do this. We will take the 0.763, divide that by 0.763, and now that's 1. And now we've got to take the 9.98 and divide that by 0.763, and that'll give us 12.96, almost 13. So now we have the masses of lead in relationship to the same mass of oxygen. And now we have to figure out, okay, well, what's the ratio between these 2? And the way we answer that question is we take the larger and divide it by the smaller. So the larger one here is 12.96. Divide that by the smaller and you come up with an answer pretty close to 2. And then obviously if we take the smaller, 6.46 divided by 6.46, we come up with a solid answer of 1. And so now we know that the ratio of lead to these is always going to be at a 2 to 1. That's the smallest whole number ratio that we have. All right, so an awful lot of time working on a couple of problems, but hopefully it would help just to recap The law of definite proportion says that a given compound always contains elements in a certain proportion by mass, and mass is really the key word that we want to deal with that, because every time we solved this, we had to figure out the mass of those uh, atoms in the deal. And then the next thing we'll look at is the law of constant composition, and or multiple proportions, excuse me. And it says when you have the same two elements combined to form more than one compound, the ratios of the mass of one element in the first compound to its mass in the second compound can always be expressed as ratio of small whole numbers. For example, 1 to 3 or 2 to 5. And that is one of the predictions that John Dalton made based on his atomic model of the atom. So maybe that helped clear up some of the confusion around the laws of constant composition and the laws of multiple proportions.